Hello everyone, welcome to another lecture of the course Digital Signal Processing. Till the previous lectures, we have been looking at the finite impulse response filters, that is the FIR filters, and we have seen its design process also. And all this discussion had started by defining an LTI system with its impulse response and then taking its Z transform and analyzing it in Z domain as well as in the frequency domain. So the point from which we had started was that any LTI system can be represented by its impulse response h of n, whose Z transform can be given as h of z, which is equal to summation n running from minus infinity to infinity h of n into z to the power minus n, and this has a region of convergence, say ROC, given as R. And in the lecture 1 of module 2, we have seen that this h of z or the Z transform can be represented using the rational form. And this rational form is given as h of z is equal to b0 plus b1 z inverse and so on up to bm into z to the power minus m whole divided by a0 plus a1 z inverse and so on up to an into z to the power minus n, and this can be written as summation k running from 0 to m bk into z to the power minus k divided by summation k running from 0 to n ak into z to the power minus k, and this summation or this expression of h of z is the standard form representation of the Z transform for any LTI system. So this is the standard form or the standard representation. That is the rational form for any LTI system. So basically what we have is h of z is equal to summation k running from 0 to m bk z to the power minus k divided by summation k running from 0 to n ak into z to the power minus k. And if we observe this expression, we can see that this expression or this Z transform has m number of finite zeros. So we have m number of finite zeros, that is the degree of the numerator is m, so we have m roots for the numerator, and if we look at the denominator we have n roots, which implies that we have n number of finite poles. Now we have analyzed the case in which the value of n is equal to 0 and the value of a0 is equal to 1. So in this case the value of h of z reduces to summation k running from 0 to m bk into z to the power minus k. So this results in a expression or a filter whose length is given as m plus 1. So basically we have the filter coefficients as b0, b1 and so on up to b of m, which is basically of finite length, and hence such type of filters are known as the finite impulse response filters or the FIR filters, whose entire design process and analysis which we have already seen in the previous module. So let us consider a simple example of m equal to 2. So what we will do is we will consider the value of m is equal to 2, and for this value of m let us consider bk is equal to 1. So what we have is h of z is equal to summation k running from 0 to 2 bk, that is 1 into z to the power minus k. So this is basically 1 plus z inverse plus z to the power minus 2, and if we take its inverse z, that is if we take its inverse z transform, the value of h of n, that is in the time domain, we obtain it as a sequence 1 1 1, where this first one is located at n equal to 0, this second one is located at n equal to 1, which is governed by this delay element, that is z inverse, and this third one is located at z equal to minus 2, which is governed by this delay element, that is it is delayed by a factor of 2 towards the positive infinity. So this is the sequence that we obtain, and we can see that this is of length L of m plus 1, that is 2 plus 1, which is equal to 3, and this is very well of finite length. And therefore these filters are known as the FIR filter. So we have seen that any FIR filter can be represented using its standard form as summation k running from 0 to m bk into z to the power minus k, and this m is known as the order. This m is the order of the filter. Now let us analyze the properties for the FIR filter. So the first one which we are going to see is causality. So if we observe this example, we can see that this h of n has 0 values for all the value of n that are less than 0. That is, for negative values of n it is equal to 0, and hence this filter is causal. So let us consider a case in which we don't have a causal filter. So what we will have is h of n is equal to the same sequence 1 1 1, but now this middle or the center one is located at n equal to 0, which implies that this one is at n equal to minus 1, and hence this filter is not causal. But now if we introduce a delay of 1, that is h of n minus 1, then now the sequence that we obtain is again 1 1 1, but now this 1 is located at n equal to 0, and now this filter is a causal one. This is the exact sequence that we have here. So now this filter is a causal filter. So what we can see is, by introducing a finite delay we can obtain causality. So if we need to comment on the causality of FIR filter, we can say that it is a causal filter, or it can be made causal by introduction of a delay. So any FIR filter is causal or can be made causal by introducing a delay. So now let us look at the second property, that is the stability. And for any system to be stable, its impulse response should be absolutely summable. That is, the value of summation n running from minus infinity to infinity mod of h of n should be less than infinity. Now this impulse response, that is h of n, is of finite duration or finite length, that is from 0 to m, and in this duration these bk's are finite values, and if we add finite values we are going to obtain a finite valued sum, and hence this condition of absolute summability is always valid in the case of FIR filters. So this condition is always valid for FIR which implies that FIR filters are always stable. So these FIR filters are always stable. Another thing we have seen while designing these FIR filters was that we can obtain a linear phase characteristics in case of FIR filters. So what we can have is, we can have a linear phase for FIR filters, and this linear phase is obtained in the case of symmetry or antisymmetry in the FIR filters impulse response. That is, the impulse response should follow the condition as h of n is equal to plus or minus h of m minus n. So basically, if my impulse response is symmetric or antisymmetric, then we obtain a linear phase characteristics. And we have seen that this linear phase is obtained for all the 4 types of filters, that is type 1, type 2, type 3 and type 4, which are based on the symmetry and the type of order, that is even order or odd order. So basically we can have a linear phase characteristics. Moreover, we have seen the entire design process of FIR filter, and we saw that it's quite simple to design. That is, we need to just have the ideal filter and then multiply it by the desired window, which depends on the characteristics or the specifications which we need to obtain. So the entire design process for FIR filters is quite simple. So designing is simple in case of FIR filters. But now these FIR filters are a special case of this standard representation. So, and it is a case in which we have none of the finite poles, that is, this n is equal to 0 and this a0 is equal to 1. So now let us consider a case in which this n is not equal to 0. So let us start with a simple example. So what we will do is, let us consider the value of n not equal to 0, and for simplicity let us consider this n to be equal to 1. So consider an example, say h of z, which is given as 1 minus 2z inverse divided by 1 minus 3z inverse. So if we observe carefully, this system has one finite 0 and it has one finite pole. So basically this system has a one finite 0 and a one finite pole. So now let us try finding its inverse. So for that, what we will do is, we will separate the numerator as 1 upon 1 minus 3z inverse minus 2z inverse into 1 upon 1 minus 3z inverse. So what we have is z upon z minus 3 minus 2z inverse into z upon z minus 3. So now if we observe this factor, that is z upon z minus 3, it is in the standard form, that is z upon z minus a. And if we consider a causal case, so considering a causal case, its inverse is a known standard form which is given as a to the power n into u of n. So if we substitute this or make use of this expression in order to find its inverse, so what we have is, the inverse of z upon z minus 3 is basically 3 to the power n into u of n minus 2 into, now this z inverse is going to bring a delay of 1 unit. So if we have a z inverse here, then we are going to have this as a to the power n minus 1 into u of n minus 1. So now the z inverse of this, that is h of n, can be written as 3 to the power n minus 1 into u of n minus 1. So what we obtain is h of n is equal to 3 to the power n into u of n minus 2 into 3 to the power n minus 1 into u of n minus 1. And now this expression, the value of this h of n is valid for all the values of n, which implies that this n, which is ranging from minus infinity to infinity, it is valued for all the values of n. Or if we go specifically and ignore this u of n, it would be depending, or it would be a one-sided function or a right-hand sided function, but it is basically valid for all the values of n that are ranging from minus infinity to infinity, which implies that the length of this h of n is of infinite, which means that this h of n is of infinite duration. Which implies that this filter, which is of infinite duration, is known as basically an infinite impulse response filter. So any filter of infinite duration is known as infinite impulse response. Or the IIR filter. So if we look at the standard representation for the IIR filter, so what we have is h of z is equal to summation k running from 0 to m bk z to the power minus k divided by summation k running from 0 to n ak into z to the power minus k, and this is the standard form for any IIR filter. And in this case, for it to be an IIR filter, the value of n should not be equal to 0. So in that case only we are going to have an IIR filter, and when we have n equal to 0, what we are left with is the FIR filter. So now let us look one by one at the properties of this filter. So the first one which we will look is the causality. Now in the lecture 1 of the module 2, we have seen that any system is causal if the number of poles are greater than or equal to the number of zeros in its set transform. So any filter or a system is causal if number of poles is greater than or equal to the number of zeros. So basically the value of n, so this n should be greater than or equal to m, and if this condition is valid, then only this filter h of z is a causal filter, which means that the causality has a dependency on the value of n as well as on the value of m, and this condition is not guaranteed every time, and therefore we can say that IIR filter's causality is not guaranteed. So as this condition is not guaranteed, the IIR filters are not guaranteed or are not always causal. So now let us look at the second property, that is the stability. And we know that for a system to be stable, its impulse response should be absolutely summable, that is summation n running from minus infinity to infinity mod of h of n should be less than infinity. So let us consider a simple example for impulse response, which is something like this. So let this impulse response be a causal one, that is, it has a 0 values for all the value of n which are less than 0, and it is decreasing in nature, that is, it is something like this. So as the value of n increases, the value of h of n decreases, and so on. So this is my h of n, which is constantly decreasing as the value of n increases. That is, as my n tends to infinity, the value of my h of n will tend to 0, and such types of filters which are decreasing in nature are basically summable or absolutely summable. That is, this condition of absolute summability is valid for this case. So such filters or systems or the impulse responses are absolutely summable. Now let us consider the second case, which is exactly opposite of this. So instead of having a decreasing filter, let us consider an increasing filter. Let us consider the case of causality itself. So we have a filter which is something like this, and so on. So basically now this is increasing in nature, which implies that as the value of n tends to infinity, my h of n will also tend to infinity, which implies that if we go on adding the value of h of n till infinity, we are sure to get the infinite value, and hence this type of impulse response are not absolutely summable. So basically, the condition of absolute summability is valid for this first case, but it is not valid for this second case, which means that if I have an impulse response which is something like this, then stability is not achieved. So similar to causality, the stability for the IIR filters is not guaranteed. So IIR filters are not always stable. Moreover, the linear phase condition for the IIR filters is also not guaranteed. So basically, the IIR filters are not linear phase. So if we look at this thing, that is the property of causality, the property of stability and linear phase for an IIR filter, we can say that these important properties which we need for designing any filter are not guaranteed in this case. So why there is a need to analyze or design an IIR filter? So the only reason that we have is if we are given a set of specifications, then the same set of specifications can be achieved at IIR filter as well as an FIR filter, but the order that we are going to get for the IIR filter is significantly less as compared to the FIR filter. So the advantage that we get So the advantage that we have for IIR filter is that if we have a same set of specifications, that is, for same set of specifications, the order for IIR filters is significantly low, as compared to FIR filters. So if we have a situation in which there is no need of causality or stability or a linear phase, then we can very well go for IR filters, as we are requiring a significantly lower value of order for attaining or achieving the same set of specifications. So for example, if we have the entire signal on which filtering operation is to be done at one go, so, or in other words, if we don't need to have a real-time operation, then in that case we can very well do away with the causality property. Or another example that we can have is, for an image, we have the entire image at one time, that is, all the values of the pixels are available at the same time. So we can very well do away with the causality property, and hence in that case it is better to go for IR filters, as the order required is significantly low. So before ending this module, let us look at the comparative analysis for both the IIR and the FIR filters. So what we have is, the standard representation for the FIR filter is given as h of z is equal to summation k running from 0 to m bk z to the power minus k, whereas for IR filters it is given as h of z is equal to summation k running from 0 to m bk z to the power minus k divided by summation k running from 0 to n ak z to the power minus k, and this availability of n number of finite poles results in infinite duration impulse response, whereas as the value of n in FIR filters is 0, we have a finite impulse response, and the length of that impulse response is basically m plus 1. We know that these FIR filters can be causal or can be made causal by just introduction of a delay, a finite amount of delay, but these IR filters are not at all guaranteed to be causal. The FIR filters are always stable, whereas these IR filters are not guaranteed to be stable. The FIR filters, or basically the symmetric and antisymmetric nature of the FIR filters, allow us to achieve the linear phase, and this linear phase allows us to have a constant amount of delay for each and every frequency component that is available in the signal or in the system response. And this IR filters does not guarantee us or does not have a linear phase characteristic. But the advantage that we have for IR filters is that for same set of specifications we obtain a lower order, whereas in order to have the same specifications, the FIR filters require significantly larger order as compared to the IIR filters, and the FIR filters are quite less precise as compared to the IR filters. So these two factors which we have seen just now, we are going to analyze it in a comparative way in the subsequent lectures by designing the FIR filter as well as the IR filter for the same set of specifications, and it would be much more clear of how these two vary and which is better as compared to the other. So in the subsequent lecture or in the next lecture, what we are going to start with is the designing of the IR filter. So what we are going to see is what is the basis of designing of the IR filter, and then we will move on with a proper procedure for design of the IR filter. So let's stop here. Thank you.